Okay, so today we will be discussing probability distribution and probability density function, very important concepts. First we start with this is probability distribution function, it is written like this. It means the probability of this. Let me explain. Capital X here is a real number in this case, and this corresponds to an event. What event? I mean, event for which this value, this variable x takes values all either equal to x, capital X, or less than x, less than equal to x. Now, probability of that is called the probability distribution function for the random variable x. Okay, f small x, capital X. So, the particular value that we have in mind is put here, and this x denotes the corresponding variable. Okay, sometimes we can be little liberal here, we can omit this subscript and just directly write f capital X or even f small x. Okay. Now, this will be clear if we give some example. Yeah, consider the example of tossing a coin. Suppose you are tossing a coin and the probability of tail occurring is say q, that is p of tail, t for tail is say q, and probability of head is p. Further, so we have got just two experimental outcomes here, t and h. Okay. Now, suppose there is a random variable x which takes the value this way, zero, okay, and sorry, x t is 0 and x h is 1. Okay, x t is 0, just a minute. Okay, this is given. Okay, now what will be the corresponding probability distribution function? It will be like this: plot this axis, this is for x, and this axis, this is for f. Now, as x goes from 0 to 1, okay, from 0 to 1, as x goes from 0 to 1, what is the corresponding probability, okay, in this range. Now, here x can be 0 or 1, up to 1, if this is tail, right. So, it is q, okay, and then it becomes 1. all right. This is the probability distribution function. Okay. This probability distribution function has got some very important properties. Let us examine those properties. Firstly, f infinity, this is equal to 1. Now, why f infinity equal to 1? It is because f infinity means p now you see, by the definition of a random variable, for no experimental outcome, x really can take the value infinity, okay, because the corresponding probability was 0, which means this event includes all experimental outcomes, because all of them are taking finite values. For all of them, x is taking finite values, right. So, that means this means the total set or total event for which the probability is 1. So, this is equal to 1. On the other hand, how about f minus infinity? Now, f minus infinity means actually, since we cannot go to the left of minus infinity, this means p x equal to minus infinity. Again, this corresponds to no experimental outcome. Okay. So, this is an impossible event for which this is equal to 0. So, f infinity is 1, this is one property, another property is this, f minus infinity is 0. Okay. Next, if you consider things like this, x1 less than equal to x2, then or rather this is less than equal to f x2. That means the probability distribution function is actually a non-decreasing function. It can remain steady or it can only go up. Okay. Now, this follows easily. After all, what is this f x x1? This is nothing but p and f x, sorry, this will be f x here, p but you see, you have given me this, which means this set it is actually contained or maybe same in this set. Okay. Because x1 is less than x2. So, set of outcomes for which x is less than equal to capital X1, that must be contained in this set, that is set of all outcomes for which x is less than equal to x2. Okay. Now, we have already seen earlier in the context of probability that for this event, if this event is contained in another event, then the corresponding probability is less than equal to, if it is perfectly contained, the corresponding probability of that event is strictly less than the probability of the other event, but since it can be same also. So, it means that this probability is less than equal to this probability, which means f x x 1 is less than equal to f x x 2, which means the probability distribution function is a non-decreasing function. This is very important. Okay. All right. Next, suppose for some x 0, consider some number x 0. Okay. If it so happens that for some x 0, f x 0 is equal to 0, then it implies that for all x less than equal to x 0, for all x less than equal to x 0 also, or let me put this way, make it capital, for all capital X less than equal to x 0 also we should have this. Okay. Again, this comes from the previous theorem that previous two theorems, that firstly f of minus infinity f x minus infinity is 0 and the probability distribution function is a non-decreasing function. Because if you consider any x which is say less than x naught, okay, if it is equal to x naught, this is already given. So, if it is less than x naught, then you have got this thing. Right. But since probability distribution function is a non-decreasing function, this implies okay. But this is 0 and this is 0, so this has to be 0. All right. So, this is property number 3. Next, you consider this, the probability of this random variable x taking value greater than some x, where capital X is any real number, that is equal to actually 1 minus f x x. Okay. Now, this is quite easy, consider these events and these events, this event, these are mutually exclusive. Okay. And this means the total set actually. Okay. This means the total set, say S, and since they are mutually exclusive and since the probability of this total set is 1, that means P of these and P of these equal to this, because they are mutually exclusive. So, P of this total set can be written like this, but since it is a total event, the most certain event, its probability is 1. So, this follows immediately, because this is nothing but f x x. So, this is equal to 1 minus f x x. Okay. So, actually these two are mutually complementary. Probability distribution function for a particular number capital X and the probability that the random variable takes values higher than capital X. Okay. Next, probability of this, given two such numbers x1 and x2, what is the probability of this? This is equal to actually okay. Again, this is not very difficult. Consider this set x this can be written as sorry, is strictly less than. Okay. These are two disjoint sets. In one case, small x lies between x1 and x2, another case x lies below x1, and their union gives rise to this set. So, probability of this will be what? Probability of this will be, if I take the probability, since these are disjoint, this probability can be written as the probability of this plus probability of this, all right. But this is equal to okay. Maybe I make a little change here at this stage. Actually, I am making a subtle change here. X is greater than x1, but less than equal to x2. Okay, greater than x1, but yeah, less than equal to x2. Then this formula will be valid actually. For that, first I consider this set x less than equal to x2. This you can decompose like this: x greater than x1, less than equal to x2, and x less than equal to x1. These are mutually disjoint. So, probability of this is equal to probability of this plus probability of this, right? But this is equal to f x x2, and this one is equal to f x x1. Okay. I think it's getting a bit dotty here, so let me erase and okay. From this follows obviously that this probability, which is this is equal to f x x2 minus f x x1. This is very important actually. All these might appear to be a bit trivial, but actually they are very useful as we go along, because actually to find out some probability of some event occurring in some range and all that, all these properties come very handy. Okay. Then another thing, I define this. This means that if you take this probability distribution function not at capital X, but slightly to the left by some, it is slightly less by a quantity which is infinitely small but positive real called epsilon. Okay, and then if you take this limit, epsilon tends to 0. So that means you are basically approaching this probability distribution function from left. Then the limit that you get, I call it fx x minus. Okay. Now see one interesting thing, that using the just previous theorem, we can always write this thing, that P of this is equal to okay. This comes from the previous theorem, because this number is greater than this. Sorry, this should be f actually. Okay, and this is epsilon. Now see the interesting thing, if on the left hand side I take a limit of epsilon tending to 0, then what happens? That is, I take a limit on this, I take this limit. Obviously, as epsilon becomes smaller and smaller, this lower limit becomes closer and closer to capital X. So, the gap between capital X and this becomes smaller and smaller. So, in the limit, small x coincides with capital X. So, this, when I take the limit with epsilon tends to 0, this goes to P x. Okay. And we have seen that if on the probability distribution function we take the limit from the left hand side, that is let epsilon tends to 0, we have a notation for it fx x minus. That means P of x, P of capital X, that is x taking exactly the value capital X, is nothing but probability distribution function up to x minus the left limit of the probability distribution function for the point capital X. That means P x okay. All right. Okay. Now, this probability distribution function can be continuous or can be discrete type. Okay. if it is continuous, that is in that case we will call it, we will say that the random variable itself is continuous, that is the if corresponding probability distribution function continuous. Now, if it is continuous, then it means, this means, you see, if this is continuous, then this limit will be same as, this comes from the definition of limit and continuity. Okay, the limit from left should be same as the value itself. What does that mean then? Means if the random variable is continuous and therefore this probability distribution function is continuous, up to here we have got this, the left limit of the probability distribution function at capital X is same as the value of the probability distribution function at capital X. This would imply from our previous theorem that probability of x taking the value capital X exactly, the probability of x taking capital X, that by our previous theory has been this, but since these two are same, this becomes 0. So, this is a property of continuous random variables, but there is another random variable called discrete random variable. Okay. Here the probability distribution function is a staircase type of function. I am giving an example. These are the points of discontinuities. Okay, say x1, x2, say this is xi, right. This axis is your probability distribution function. This will be the case of a discrete random variable. Okay. In this case, you see the function itself is not continuous, there are discontinuities. What happens then at these discontinuities? You see, up till this point, that is just at the point when we are about to go to x2, till that time this probability distribution was giving simply the probability of one event, okay, and then at x2 there is a jump, there is a discontinuity, right. So, what is, or instead of x2 say consider xi. If I say what is the probability of x taking xi exactly, this by our theory would be this. Now, you see what is the meaning of this. F x x I means what, this is a distribution function, that means probability of x's taking value up to xi, that is either xi or any value up till this, that total probability is this. And what is this left limit? Left limit is nothing but the probability of this variable x taking value up till xi, but excluding xi. Okay, so this difference will be exactly equal to the probability of x taking xi. You can even call it pi. Okay. This is the case of a discrete random variable. Okay. Now, from probability distribution function, we actually go to something more interesting and more widely used, and that is called probability density function. Okay. Here sometimes we do not by f, sometimes by p. My notation should be rather p, because p stands for probability actually. So, I would prefer p. Px, it is nothing but the derivative okay, here for simplicity I am just writing it as a function of small x, okay, this probability distribution, and deriving it with respect to x. This is called the probability density function. Okay. One interesting thing you can see, that suppose this is a continuous function, then of course we have got px as continuous. Okay. But suppose fx is a staircase kind of function, that is the random variable is a discrete random variable. In that case, this derivative will be 0 everywhere except at the discontinuities, and at the discontinuities there will be impulses, right, Dirac delta functions, impulses, each multiplied by the probability of x taking values at those discontinuities, that is px, okay, for a function like this. Let us once again draw. function like this, x1, x2, x3 and things like this. This for the probability distribution function. Okay. Corresponding Px should be like this. We have one impulse here. Its strength will be P1, where P1 is the probability, exact probability of x taking value equal to x1. Then there will be another impulse here. Okay. Then another impulse here and like that. P3. This is again x1. This is again x2. This is again x3 and like that. So that means we can write in general Px is nothing but summation of Pi delta x minus xi, okay, and this is over some I. And what is Pi? Where Pi is probability of x taking value equal to xi. Okay. This for the discrete case. So, remember for a discrete random variable, the probability density function actually is a linear combination of some impulses. Okay. It will be interesting to consider some standard probability density functions like normal distribution or uniform, okay, and things like that. Okay. Number 1, normal we call it mu, sorry, this is also Gaussian. Sometimes it is called normal, sometimes it is Gaussian. Its formula is Px okay. It might look complicated, but it is one of the most widely used density function, especially in communications and things like that. Okay. These two parameters mu and sigma, they have their respective interpretations, respective meanings, which we will study later. Mu is called the mean and sigma is called the standard variation, or sigma square is called the variance of the random variable x. Okay. Now, since we have not defined these things, I am not getting into that, but this is the typical form. You can see one thing, that since there is a square term here, this will be symmetric around mu, that is whether x minus mu is positive or negative, we will get the same value, right. And when x equal to mu, then only it will have its peak value. Then as this difference increases, since it is coming with a negative power, this decreases. So, it will be having a peak value somewhere at x equal to mu, and then as you go to the right and to the left of mu, it falls down. Okay. So, typically it will be like this. it is actually a bell shaped curve. Is occurring at mu, okay. Sorry, this is Px, this is x, okay. And one thing we have seen that what is Px after all? It is the derivative of fx, okay, which means this is nothing but integral of Px dx from minus infinity to capital X. Okay. That means fx infinity is nothing but integral of this from minus infinity to infinity, and since that is equal to 1, you know, we have this thing this is equal to 1, which means this probability density function has a total area under it equal to 1. So, when integrated from minus infinity to infinity, the total area should be equal to 1. Okay. That is the case here. For this case, actually the corresponding distribution function would be like this. To get the distribution function, you have to go on integrating, right? And as you go on integrating, area increases. So, distribution function will go up, and finally, when you have come to this sort of values close to this, after that even with some increase in x, the value of this probability density function has fallen down so much that the probability distribution function does not increase much, it sort of remains steady. Okay. So, initially there is a growth like this, okay. Your mu would be somewhere here, okay. But as x increases, finally this approaches 1, okay. This is for the Gaussian case or normal case, okay. There are many other interesting examples. Today I will consider one more, uniform, and few others like binomial, Poisson, Erlang and all, that we will consider in the next class. So, another example, again quite widely used, I would say, of a probability density function is that of uniform distribution. Okay, this means in this case sorry this is something like this, you know, take two numbers x2, x1, within this density function has a constant value, but to the right of x2 and to the left of x1 its value is 0. Obviously, since the total area under this curve has to be equal to 1, okay, then you can find out how much should be the height. This width is x2 minus x1, so height should be 1 by x2 minus x1. So, here I am rather writing minus and plus because there is a discontinuity here, okay, and this is equal to 0 elsewhere. So, this is for the probability density function, and corresponding probability distribution function will be what? We have to go on integrating it. Okay. What will happen if you integrate it? Up till now, up till this point 0, then as you go on integrating, the area increases. Finally, at this point, area attains maximum, and that is equal to 1, and then it remains steady, right. So, probability distribution function should be like this. It is going up linearly, okay. Like this. Okay. So, this is for the case of uniform distribution. Consider the discrete case. Suppose that there is a random variable, let us consider what is called binomial distribution. Okay. Suppose there is a random variable x, okay. We call it that it has a, we say that it has a binomial distribution, has a binomial if it takes the values only this, either 0 or 1 dot 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 up to n with the corresponding probability like this. Okay. These are the probabilities. This is n c k p to the power k q to the power n minus k. Okay. One thing you see, where of course p plus q they are equal to 1. So, if you really sum up, that is p of x equal to 0, then x equal to 1 up to x equal to n, and add them, then we get a binomial series p plus q whole to the power n, and since p plus q equal to 1, you get the value 1, which should be satisfied because x can either take this or this or this, x cannot take anything else. Okay. So, total probability should be equal to 1. Okay. So, this is called binomial distribution of order n. Okay. Of course, these are only the probability values for x, I mean probabilities for x taking either value 0 or 1 or 2 and things like that. Okay. But when it comes to the density, then as I told you earlier, you need to add like this. Okay. So, this is for binomial distribution. Now, there are other distributions also, Poisson distribution, then Rayleigh distribution, and which are of course very useful in communication or time series modeling and weather prediction and things like that. Okay. Since we do not have much time now, we will consider them in the next class. So, in today's class, just to sum up what we have done, we have started with probability distribution function, its definition, characterization. We gave some example for this probability distribution function. We discussed various properties, like the probability distribution function at x equal to infinity has value 1, at x equal to minus infinity has value 0. Then probability distribution function is a non-decreasing function, that is, it can only go on increasing or it can remain steady, it won't go down. Okay. And then some more properties were discussed. Okay. That is, if there is a random variable which takes values between two ranges, two figures x1 and x2, the probability that the random variable will remain between x1 and x2 can be described as a difference between the two, the difference between the probability distribution function at x2 and x1. We discussed what is meant by continuous random variable, what is meant by discrete random variable. Okay. Then we gave a definition of the probability density function and gave certain examples like Gaussian, and Gaussian also is called normal distribution. Then give the example of uniform distribution and concluded with binomial distribution. So, in the next class we will be taking few more examples of these distributions. We will carry out some examples also, and then we will go into conditional probability density and distribution. Okay. So, that is all for today's lecture. Thank you. In the last class, we discussed probability distribution and probability density function, and discussed the properties of probability distribution function. Okay, and then we considered some examples of probability density function, like normal, that is Gaussian density, then binomial distribution, that was a distribution, and we considered the corresponding density also, probability density function also. Then we considered binomial, okay, we considered uniform probability density and all that. Okay. We, in today's class, we start from that. We consider one more probability distribution function which is very useful, especially in queuing theory and network related problems. That is called Poisson distribution. Here x, it takes values like 0, 1, 2, dot 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 k, dot 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 dot. Okay. The probability of x taking k will be given as e to the power minus a into a to the power k by factorial k, where a is a parameter. Question is, can a be negative? You see, a cannot be negative. It is because if you consider this negative power, odd powers of k, odd values of k, that is odd powers of a here, say to the power 1 or to the power 3 or to the power 5 and all that, then obviously if a is negative, the entire thing becomes negative, right, and probability cannot be negative. So, from in the definition itself, it is implied that a is a positive number, okay, and depending on the a that you choose, you get one particular distribution or other, right. So, if that be so, there is a corresponding probability density function. See, this is just a probability, it is not even probability distribution, it is just the probability of x taking k. So, corresponding density function, as we discussed the other day, will be what? There will be impulses at 0, at 1, at 2, at k, and like that. Okay, and each impulse, say an impulse at k, and the other case other range, x less than equal to b. In that case, what is happening? Our m is giving us this, and what is the intersection here? Capital X is less than equal to b, whereas m corresponds to those x which lie in this range, greater than b, less than equal to a. So, intersection is phi empty, for which probability is 0. So, clearly this will be 0. Okay. So, corresponding density will be what? When this probability distribution function is 1, that will be 0, when this is 0, that will be 0, and in between it will be just derivative of this, and then derivative will be what? That is for x greater than equal to a, and also for x less than equal to b, p of x by m 0, and for x greater than b less than a, p of x by m will be p of x, because you are deriving, it was f x minus f b. If you derive, you get p x only, and the denominator you get f a minus f b. So, that is all for today, and we have covered enough of this topic on random variable and probability density and distribution functions and their properties, then conditional probability density, conditional distribution. We have just to consider what is called total probability distribution and all that. We will take up some few examples in the next class, and then we will proceed to what is called function of a random variable. So long we have been dealing with only a random variable, then you have to consider function of a random variable, like I mean, if x is a random variable, then and its probability density is given, but then x square also is a random variable, what will be its probability density function, and likewise. Okay. So, that will be done in the next class. Thank you very much.